In a recent segment, I told you that KSP equations mean that there is a maximum concentration that a compound can achieve in solution. Let's figure out how to solve for that maximum concentration for this example we've been working with lately, silver chromate. In particular, we know the KSP, 1.2 times 10 to the negative 12, because as you saw at the end of last segment, we could either measure it experimentally if we were careful, or look it up from a literature source, such as table 9.4 in your textbook. So, how do we approach solving a problem like this? At first, looking at this problem, you might be saying to yourself, there's not enough information here to get started. When we looked at problems involving buffers or weak acids, there was always a lot of information about concentration, or at the very least maybe a number of moles. There doesn't really seem to be very much here. How do we approach it? Well, we're, as always, going to need our equilibrium expression and our chemical reaction. So, in our last few videos, we looked at how to determine that equilibrium expression. How do we use it now? Well, the key is to use an ICE table. We saw with the example of things like buffers that ICE tables were a great way to organize our thinking and figure out what's going on. And the same is going to be true here. Let's put the various parts of our reaction into our ICE table. Is there anything that shouldn't belong in this table? Well, remember, we're talking about molarity here, and our solid isn't dissolving. It doesn't have a molarity. To put it another way, it's not showing up in our equilibrium constant expression. So you have two options here. You can either do as I'm doing here, write this in and then draw a big ol' X through it to remind yourself that it's not going to be relevant, or you can just completely remove this column. That is, don't include it in the table. Okay, what else do we know? Well, we know that if we're trying to figure out how much dissolves, to begin with, nothing dissolves. Well, what else do we know? Well, we also know that these are linked together stoichiometrically. For every 1 mole of chromate that dissolves, we also have to dissolve 2 moles of silver. That means that though these amounts that are going to dissolve are unknown, we do know something about them in that they must be related. So, if we add 0 to 2s, we get equilibrium concentrations of 2s and s. Let's plug that into our KSP expression. Now you might be feeling a little bit more comfortable. We can use that value of KSP that we got previously from our table, and we can distribute these through. 2s squared makes 4s squared once we distribute it through, times s. This equals 4s cubed. I would say the most frequent mistake that folks make when working on problems like this is neglecting to square that coefficient, or do whatever power is present. Now, we actually do have something we can work with. Dividing both sides by 4 will bring us down S cubed. And we can now take the cubed root of each side. You'll want to make sure that you know how to use your calculator to take roots that are larger than 2. That is, many calculators have an easily located square root button, but you'll also want to make sure that you find the button to do things like cubed roots. If we do that root, we find that S is equal to 6.7 times 10 to the negative 5 molar. This is the most concentrated solution of silver chromate that is possible.